Okay, I will go through assignment 30, but first I will introduce the assignment. So this assignment is about modeling a river, and this river has been split up in several reaches. So we have 8 reaches, and for each reach different things can happen. So we have, for example, here some agricultural runoff, and we have here a tributary stream going into the river, and we have some drinking water going from the river to the city, and some wastewater and industrial wastewater, industrial use, and so on. And this all happens at different stages in this river, and we will model this by first looking at each of these reaches one at a time, and we will be now you can, and we will use this plug flow model for this. Okay, so here you can see some information about the different reaches. So you can see how long it is. You can see the width and depth on that part of the river, and the agricultural loading into the river, and so on. There's different values here that you need to use, and so information about the system is mainly from this table. Then we use the reactor. The reactions that are happening is again these the generation of organic material, which uses oxygen, and we have oxygen uptake, and we also have this added organic material from this agricultural runoff. So this is different settings that are for the system, and you can see here some of just explanations of the different values or different parts that are for example, part of this runoff. Okay, so for each of these reaches, we will be modeling it as being first a mixing point, meaning that if there's some additional flow into the system, we will be modeling this as being the concentration, the two concentrations in. So the part of the river that is already there. So just if we are looking at, for example, this from 3 to 4, we will see that the river initially has some kind of mixture of concentrations, but then we have this tributary stream going into the river, and this will have it may have different concentrations of oxygen and organic material, and that means that we need to model how will the concentration look after this addition of this tributary stream. And you can see here that the C out, the concentration, will not just be the addition. We have a small cross over this equal sign. So the C out will not just be the addition of the concentration at one of the inputs plus a concentration of the other input, because there will of course be a dependence on how much volume of this concentration is actually being mixed. And these are values that we will then be able to read from this table here. But for each reach we have this mixing point, and we also have a splitting. We can also have splitting point, meaning that if we have the situation where some water is diverted away from the river, so for example at this drinking water point here, or in this industrial use water point here, then water is taken out of the system, and that of course also means that the volumetric or the volume of water will change, and that will have an effect. So let's see. Yes, so here we can see a sketch of how to calculate this, but the main strategy is this to divide each of the reaches into a mixing point, a splitting point, and then a system going for a specific amount of meters here. So let's say we have a mixing and a splitting point at this beginning here, and then we can define some preliminary values at this point here, and then we calculate how will the system react in this reach, and then get some values as of how the system looks when we reach the end of the reach here. And then we can use those values to initialize how reach 2 will be initiated, and then we have the information to calculate how the system will react during this reach 2. And so a combination of whatever is in this table, and also whatever we arrive at when we analyze the system. For example, for the first part here, we analyze it and we get some values for the concentration and the volume and all that at this end point here, and then we use those for initializing the second step, the second reach here. Yes, so you can see that here, this is formulated here. You can see that you can make some initial calculations, but I think I will take that as it comes down here. Yeah, so we need to model this system, and then we also need to plot the results. So the thing that should be plotted will be the concentration of organic material and of oxygen, and how the volumetric flow will change, how the speed in the river will change, and how the area will change. And we should do that with respect to x, so meaning just having all these values and how they change along the river. And using this increment of 1 meter, I don't believe is that important, because Mathematica will be able to just give us functions that can calculate this for us, and it doesn't need this statement of how much increments should be used. Okay, so switch to my solution here. Okay, so first of all, at some point we will need all the information from this table. So this one needs to be put into Mathematica. And you can see here, first of all, I make a list here, simply having the number from 1 to 8, which I will be using to, for example, say, to get an index of what reach I'm working on. This is mainly just to be able to use this list here as going in as a table, so that I'm able to change the index values here, or go through all the index values here, and these index values will then be used in all the other lists. Okay, but here you can see that I've put in the length, so you can see this is just the length that is stated here in this table, in this column here, and so also with the width and the depth. And then I create this area list. So this one area is not in here anywhere, but it is simply just the width multiplied by the depth. So this gives the area, and this one I can pre-calculate, so I've done that here. And then there's this agricultural load, and here I've just created a table, a list with zeros. So here is a list of zeros from 1 to 8. This is just a way of creating a list of 8 elements, and then I set the first element to being 0.05, which is from the list here, agricultural loadings. And you can see I have the list here, so mostly zeros except for the first. Then I have my volumetric attributaries, so also from the list. So you can see at the first and second reach we have no addition of volumetric flow, but at the third, sorry about that. Okay, so I was just going through these lists that I built. So they are mainly just from the table here. And yeah, this was the the addition or subtraction of volumetric flow that happens throughout this system. And you can see, for example, that so that the third and fourth, there are happening something in the third, something is subtracted, and in the fourth it is added and subtracted, added. And if you go up here, you can see that for the third we have this drinking water, meaning we have some subtraction. In the fourth we have this tributary other creek or something else running into this, and we have this industrial use that is subtracted from the flow rate, and have other things that are added. So that's how this, or what this means. For whenever there's a minus, it means that we are subtracting something, taking something out, and a plus means that we are adding something. Okay, and then we have down here the concentrations at the different concentrations of the organics at the different parts of this of the river, so, or at the different reaches. So you can see here, this is kind of written in a maybe weird way, but this is just saying that for the first and second we have no, the concentration is 0, but that is just because we have nothing running into the river. So you can see up in the volumetric flow attributions, additions, we have zeros for the first two, so we also have zeros here, and also for the oxygen additions, the concentration of oxygen also 0 here. But then from the third, since we are taking something out of the river, the contribution here is the contribution or the result. How can you say? Anyway, the organic material concentration here. This is simply just the organic material, and that is what this function gives us. This gives us the organic material, and then it's for the time, or for the place with the respect where x is the place at some point in the river, and this point is simply just the two first of the length here. So after 1700 and 1970 meters, those two added, we have this. We need to know this concentration of organic material, and that is what this function gives us. And this here is simply just doing this addition in a maybe a little weird way, but this is simply just adding those two numbers here, so 17 and 1970. Then we have for the this will be the fourth reach. We can see here that it says 5, and that is because we have a 5 here, and you can also see here that for the fourth or third, we have that the reach, the concentration of organic material is simply just whatever was exiting from the second reach. So that's why we are using this function to calculate the output from the second reach. And then we had 5. This was from the table, and then again we need to calculate the concentration of organic. Actually, the concentration of organic, and you can see it's totally this. It's the same for the oxygen concentration here, but we then need the concentration of the organics from the exit of the fourth reach. So that is again calculated by using this function here, which is a function I will define later on. But this function simply gives us the concentration of organics at a certain point, and now we are adding from all the reaches, or the length of all the reaches from the first to the fourth reach. So meaning this number plus this number plus this number plus this number. Yes, so we are adding all those, and then we have concentrations because of some inlets, something that is added to the river. 400, 700 and 1200, and and that is because of these different treated water and industrial wastewater and industrial waste. So they are all added, and they have these concentrations of organic material. Okay, and the oxygen concentrations are the same, again using not a function that gives us the organic concentration, but this time a function giving the concentration of oxygen. And then I create these two helper lists. They simply state the value, where each of the reaches start. So the first reach will start at 0 meters, and the second will start at 1700 meters, and so on and so on. And this second list here simply states when each of the reaches will end. So here we see that the first reach will end after 1700 meters, and the second will end after 3670 meters, and so on. So these are just lists that I will use later on for in helping of the calculations. Okay, and then I just copy. So this is just a copy from assignment 29, because I again need this function, this equation 3, that simply states, I can just evaluate this to recap, that this states how the concentration of the J component will change with respect to X, and that of course again depends on the rates, reaction rates, and the speed. Okay, so I state the relations, and you can see here we have this round off, that is this agricultural load that is put into the river. We state the constants, and we created the equations here. So for the organic material, and for sorry for the interruption, but the two equations for the oxygen and for the organic material as this, and you can see here that now this runoff or agricultural load is added. And then we are able to state or create this our calculations, differential equations system here, and we have initial additions here. Okay, so now comes the more or less tricky part, because now I need to model this system, and I need to do all this with first having to have a mixing stage, and then so where it was here, so having a mixing point and then a splitting point, and then after doing that I'm able to have the initial conditions for the reach, for the current reach that I'm working on, and then calculate how the system will react along this reach. So this is what I do here in this. I do this with a do statement, and you can look up this do statement, but in it's simply just a looping statement, more or less like a table. I think I could probably just have used a table here, but I will use this do statement. And you can see here that I declare a variable here named reach number, and this reach number variable will take on all the each of the values in this reach lists, and the reach list was the one that I created at the beginning here, that just has the numbers 1 to 8. So this variable reach number will take on values 1 and then go through the statement in here, and then take on the number 2 and go through the statement, and so on. But first I create I assign initial values. So we have this initial volumetric flow. So I call that V in as being as saying that this is the volumetric flow here at the beginning of reach 1, and this is given from the assignment text, I guess, at some point. Yeah, here. So volumetric flow at 0 is equal to 1000 cubic meters per hour. So down here, yeah, I state that here, and I state the concentrations, and I state function values for this CA, the functions that tells me concentrations at different places, or for different values of x. And here I just state that for x equals 0, I have these concentrations here. So this is just another way of stating initial values. And then I prepare these lists. So I have lists here, COX list, and this list, let's see. Yeah, this list will contain all the subparts, or all the parts of, it will contain several interpolating functions for each of the reaches. So yeah, that will make sense later on. And I have the same here for this organic material. So empty list, but this list will at some point be filled with interpolating functions for each of the one interpolating function for each of the reaches. And then I have some other lists here again for the volumetric flow and the speed, and they will also be filled with they will not be filled with interpolating functions. They will simply be filled with values, because for each during the reach I will not have any change in the volumetric flow. It is only in the mixing and splitting states that my volumetric flow will change, and that's also the case for the speed. Okay, so here I calculate the split. So when I have a split, you can see here that I have no change in the concentrations will not change. So I'm just splitting out, taking out some of the water, and and I do that by saying I take the V in, meaning or saying that my V out. So after the split, I will have a volumetric flow that is equal to the V in plus the added volumetric flow, and I do that by using this reach number. So for the first iteration of this do statement here, this reach number will be 1. So I'll go into this volumetric flow trip list that I stated up here. Let's see here, and I will take out the first element. And since that's 0, this means that for the first run through, this will be 0. So my V out will simply be my V in. So nothing is added here, or split here. Nothing is split here. I have my speed, which will be my V out, the one that I just calculated, divided by the area. And the area is again is this list that I created, where I go in and find out, take the first element out of that list. So being the area, the cross area for the first reach. And this area again was something that I calculated up here by saying width multiplied by depth, and you can see here that I have now 8 different values for the area. So that gives me a speed, and now I put these values into my lists, respectively the volumetric flow list and the velocity list here. So now I calculate the mix, and the mix will depend on the if we are adding or subtracting any kind of volumetric flow. and it will be multiplied by the concentration of that flow if it's something that's running into this system. If it's something that runs out, you will see that if I go up here, I will simply set the concentration to 0, meaning that this part of this part here, when I'm not having anything flowing into the system, this will simply means that this one here will get this one will be 0, and multiplied by whatever is in here is not really important because it will just be 0 anyways. So as long as my concentration of my added the concentration of whatever is added, as long as that is 0, it's essentially the same as not adding anything. And I'll do that both for the two reactions. For the two additions. So in my mix here, I can say let's see. Let's see here. So this is the mix thing that I have, that the concentration out is not just the concentration of the two things that are going in, meaning the flow of the river plus any additional flow, but it's actually dependent on the volumetric flow, and that is why I multiply by the volumetric flow here. And I do that here, and I also use this value that I calculated or that I set up here, because that is the input for this. And then I use this one here. I use my CS function to get out what is the concentration of the river at this point. And when this one is 0, I will simply take out the reach starting point, which for the first one, meaning when this is when this is 1, which it will be at the first go through of this loop, the first iteration, I will take out a 0, because I will take out the first element of this list, which will be a 0. So meaning that I will get the concentration with this concentration function. I will get the concentration at the displacement or the x value equal to 0, and that is what I set here. So this is another way of stating the initial value. And I do the same for the oxidation or the oxygen concentration. So this was the mix state, and you can also see that I divide by the V out here, which makes sense if we look at it as concentration, what's it called? The preservation of the mole balance, as it was called, or the that is actually what is called. Okay, so now I have figured out how is the system looking at the beginning of the reach. So now I'm able to formulate my system of equations here, where I use what I found out up here. So you can see here I use this concentration of oxygen as the initial condition for the concentration of oxygen, and I use the concentration of organic material as the initial condition here. And again here I'm using these helpful lists that I created earlier to get out the starting point and the only the starting points here. I'm using the other list here to get the ending points, not there but here, to be able to know when should for what region should I evaluate, or should I get the solution for X. So this one gives me the solution in the first run when reach number is 1. I will get solutions for when X goes from 0 to 1700. Okay, and then I get the results, and they are stored in these function values here, also these variables here, and then I take these variables and append to this list, these two lists here. So here I'm adding actually a function to this list, and I'm adding another function to this list. So here's how this is why I end up with these two that I initiate here, up here, these two lists of oxygen concentrations and organic material concentration lists. They will end up being lists of functions. So those functions I added here. And then I simply prepare for the next iteration. So now I say that I started by putting 1000 into my Vn here. But after the first iteration, I have a new situation for my Vn. So my Vn for the second reach will be something else that the 1000 here that are stated here, and they will simply be this V out that is calculated here. So I put this V out in my Vn, and now I'm able to start over. So start up here again, where my reach number now will be 2 instead of 1. So now I can calculate a new V out, where I use this Vn that was overwritten in this line here, and plus that with the added volumetric flow from now reach 2, because now this reach number will be 2. So now I will go into the second element of this list, and I will do the whole thing over again, and then I get some errors or some warnings here. I don't believe they are that they pose any problem. I'm not really sure why they are there, so I might need to go into that. But anyway, running this, I'll just do it on the notebook. Running this, you can see when I write my COX list, you can see that I get interpolating functions, and you can see that I have 8 interpolating functions, and that the ranges for these interpolating functions are the reaches. So the first one is from 0 to 1700, and then from 1700 to 3670, and so on. So this covers the whole reach, or the whole river part that I'm modeling. So now it's simply a matter of plotting. And since I have these 8 different functions, therefore that covers 8 different parts of the reach, I'm simply just plotting them all in the same coordinate system, and you can see that I get these not continuous, but definitely not continuous, and also not connected part here, but they all cover they together cover from 0 to 12,000 meters of this river, and they are changing going up and down the concentration. And you can see here for the first part, for example, when we had this agricultural offload, that we have that the concentration of organics is rising, and then in the second part, the second reach, we had no interference. So here we just have this organic degradation process going on. So here we have that the concentration falls, and then falls more rapidly, probably because we are mixing with something. Let's see. No, we are actually just taking something out, but that might be because our area is changing or something like that. So there's different things will get into. We'll have something to say here, but here you can see how it evolves, and also the concentration of oxygen, how that evolves. And here you can see how the volumetric flow changes in the system, and how the speed changes here, and how the area, the cross-section area of the river changes. that was what we were asked to plot in this second part of assignment 30. So I will end here. I hope this makes sense. Otherwise, you are welcome to either ask questions in the Google Doc, or we will also be talking about this in the next lecture.